Thank you for the invitation, and very nice to meet everyone, at least virtually as well. My name is Emaad Paracha. I am currently a PhD candidate, completing my PhD in physics with a specialization in astrophysics at the University of Toronto. And I am part of the Superbit team at the University of Toronto. So let me give you a quick introduction of Superbit and of our team and what we do and my research as well. So this is a picture of me along with the part of our crew and the telescope that I work on. It's called Superbit. Like I mentioned before, I'm currently pursuing my PhD in physics, specializing in astrophysics. Oops, take it forward a bit. And I collaborate. This is not just a University of Toronto effort. We collaborate with Princeton University and Durham University in the UK, along with NASA and the Canadian Space Agency. In the beginning, you might have actually seen several of those. If I just go back here, you'll probably have seen several of those logos up at the top. We partner with the Canadian Space Agency, CNES, which is French, the French Space Agency, and NASA as well. And there's also other people who are part of our group as well. This is, I guess, skipping a bit forward, but I'll be talking about what my research is, but this is part of the team. I would say this is about 30% of the, not 30%. This is about 70% of the team that we have. And this is a picture that we took with the then NASA Administrator Bill Nelson and Deputy Administrator Pamela Milroy in 2023. Now there has been a change with the change of the administration in the US, but they were the NASA Administrator and the Deputy Administrator, and this is the Superbit team. So I mentioned Superbit. I've mentioned that I'm currently doing my PhD in astrophysics, but what is my research and what am I doing? So to preface that, I want to start off with mentioning, and if you can go to the next slide, I did press next, but I don't think it clicked. Perfect. So many of you, I'm sure in the room, and many of you have seen the night sky through a telescope. You've probably looked up. You've probably looked up at all the whether you're in a city, whether you're outside of a city, you've probably seen the night sky. You've probably seen stars. You've definitely seen stars. You've definitely seen um, maybe you might have seen the Milky Way, or at least outline of it. Or if you ventured out of the city, you've probably been able to see even better and a lot more stars and a beautiful night sky as well. And this is something that we need to do, looking at uh, not just for looking at stars and galaxies, but also to research. And there's a big problem. The problem is that we're not able to see, if you go to the next slide, we're not able to see the night sky easily through a telescope on the ground. Um, can you go to the next slide? Perfect. So, many of you might have tried to actually see the night sky through while you're in a city and you're not able to see much outside. If you go out of the city, you're able to see more. And there's not just light pollution that we have to worry about. There's also, if you go to the next slide, there's other kinds of pollution as well, like thermal disturbances. If there's a very hot day, you might notice on the hood of your car there's these heat waves that are rising, and you'll see thermal disturbances. Or there could be atmospheric pollution, especially today, with how it is in Toronto right now. We're not able to see much outside. Even if we get out of a city, even if we get out to the middle of nowhere, yes, we'll be able to see more, but there's still all these effects that are a problem. So NASA decided to work on a telescope that evades all of these. And the most natural place to go was space, where you're above the entire atmosphere. So if you go to the next slide, which I'll take a guess and I'll say probably all of you have probably heard of it. This is a scope up in space. It's an optical telescope, so it looks in the um, optical spectrum of electromagnetic spectrum. And it is built to overcome all of these issues that come with ground-based telescopes. Uh, Ground-based telescopes, again, have to deal with light pollution, wind pollution, atmospheric pollution. In space, they don't have to worry about it because you're above, you don't have the atmospheric effects or ground-based effects to worry about. You're in a cool environment where you can image and get really, really high resolution. And actually shown some of those pictures that Hubble has taken as well. Those are uh, those when they were in the 90s and the 2000s and even today, those are some of the best images that we have of space. But if you go to the next slide, space is extremely expensive. I think the slides are jumping around. I don't know if oh, perfect. Okay. But the problem is space is extremely, extremely expensive. Um, Hubble had to be launched up in a balloon. Sorry, Hubble had to be launched up in a rocket. I'm actually jumping ahead of myself. And it cost an insane amount of money. And I'll actually, in the next slide, that actually shows how much money Hubble cost. But it was sent up on a rocket, and it actually had to have astronauts go up to fix Hubble as well because they had an issue with their mirror. Hubble cost $15 billion over the course of its lifetime, and it still costs to this day because there are people still maintaining it. However, if one of those stacks of $100 bills is $5 million, which I mean, you can debate how many houses it is, but let's say it is five houses. That's how many stacks it would take to create Hubble. So the problems with Hubble now are that it is also coming to end of life, and it is very, very, very oversubscribed, which means there's a lot of research requests because it is one of its kind. It is one of the only telescopes that is really good in optical, especially in the blue wavelength up in space. James Webb Telescope is another one, yes. However, it is more focused on, or it is more geared towards the infrared and the red side of the electromagnetic spectrum. However, Hubble is one of its kind and it is very oversubscribed with a lot of research requests. And since it is coming to end of life, NASA needed to come up with a new telescope. And this is where our research came in. So if you go to the next slide, what we decided to do and what our lab at the University of Toronto decided to do was to build and launch a balloon-borne telescope where we actually go to near space for much cheaper and we're able to get nearly as good resolution as Hubble does because we're above the atmosphere. So we're trying to match the best of both worlds with ground and space telescopes where we have the resolution of a space telescope because we're above the atmosphere but at the cost of a ground-based telescope. So if you go to the next slide, let me talk a bit about the balloon and then I'll talk about our actual telescope as well. So you might be thinking, what kind of a balloon is it? How big is the balloon? How big is the telescope itself? I just had a picture, and that was a picture of our telescope, super big telescope. But these balloons are essentially helium-filled balloons, just like you would have any birthday balloon, except they're nearly 100 million birthday balloons. So if you take 100 million birthday balloons, if you might have seen the movie Up, um, where they're going up in balloons, or you might have just played with a birthday balloon and left it, and then it goes up into the sky. This balloon is nearly as big as 100 million birthday balloons, and you can, when it is fully inflated, you can actually fit a football stadium inside of it. That's how massive this balloon is, nearly 40 million cubic foot of helium. And there at the bottom is our little telescope attached to it. Now, if you go to the next slide, so these balloons, think of this as a very massive birthday balloon. This goes well above where normal airplanes fly. So this is an infographic showing where the top of Mount Everest is. Normal commercial airliners fly at around 10,000 meters, around 30,000 to 40,000 feet. Our balloon and our telescope, they go up to nearly 30,000 meters. So nearly 30 kilometers, actually above 30 kilometers. between 30 and 40 kilometers, which is nearly 3 to 4 times higher than commercial planes go. And there we're above 99.7% of the atmosphere. And in a few slides, I'll actually show a picture of that. And the whole goal of that is to get above the atmosphere so we don't have atmospheric effects, atmospheric distortions in the light that we see from stars coming down. So if you go to the next slide, I'll quickly show as soon as the balloon is launched, it is about 1% inflated, but as things rise, they expand. And you might have noticed this if you take a bag of chips, and if you go up a mountain, if you're driving up a mountain, let's say the west coast of Canada, you'll actually see the bag of chips expands as you're going up the mountain because of the decrease in pressure. So when the balloon is initially inflated, it is only inflated to 1% at launch, and then it expands as it gets to floating height, and then it expands to the size larger than the size of a football stadium. If you go to the next slide, you'll actually see if you've ever filled up a balloon, if you ever filled up a birthday balloon by yourself, this is how we actually fill up this balloon. And there's actually two balloons. The second one is a tow balloon to stabilize the original, the main balloon as well. But this is how we're filling up helium into the balloon on the day of the launch. If you go to the next slide, um, and this is again just showing the massive size of the balloon and how big it is. If any of you have ever been lucky enough to see one, or if any of you have ever seen a picture of one, you can fit 195 Goodyear blimps inside one of these balloons. So just to showcase how big these are and where they'll end up, I'll show that in the next slide. But before that, I have a video, if you go to the next slide, of one of the launches and how we launch it. Let's see if the video plays. See if you can click it. Oh,
Sorry, Emaad, does not seem to be playing. Do you want to keep going?
sure. I can keep going. That's not a problem. But if any of you are curious, I can definitely share the video afterwards as well. But as it launches, that was just a video showing how it launched and how our telescope launched as well. But as it launches, and when it is at floating height, it is above 99% of the atmosphere. And you can see that blue glow. That is actually the Earth's atmosphere. That is our sky. That is the blue sky that we see outside. So what we're trying to do is we're trying to show how we can get alternative methods to get to space, or near space, if you will, but for cheaper. Instead of on a rocket with jet fuel, we go up on a balloon instead to this height where we're above the atmosphere. So that's about the balloon, but then now what it was our telescope and what did we build? So if you go to the next slide. Oops, this should have been the other way around, but that's okay. The Yes, that's a better view of the telescope. But if you go back to the slide, I'll talk about SuperBIT. So SuperBIT stands for Super Pressure Balloon-Borne Imaging Telescope. It was jointly developed by University of Toronto, Princeton, Durham University, with assistance from NASA, JPL, the Canadian Space Agency, and the French Space Agency. It was actually started in 2014 by the lab where I currently work at the University of Toronto, which I joined in 2020, but they had 4 test flights before I joined, 2 in Canada and 2 in the United States. And we had our science flight, which I was a part of, and I was part of the team in 2023 from New Zealand. If you go to the next slide. So for the techies out there, it is a 0.5 meter telescope, f11 telescope with 0.05 arc second stability. And I'll actually talk about a bit about that and what that means. Because as you can imagine, if there's a telescope it's trying to take pictures of the sky, you want to ensure that it is stable as you're doing long exposures. You might have tried that with your phone as well. If you take your iPhone up, point it to the sky, you try to hold it straight, or if you ever try night mode, Just holding it steady, it's such a hard thing to do for 3 seconds, while we had to ensure that it was held steady and pointed for 5 minutes, which was our exposure time. Like I mentioned before, it's above 99.7% of the atmosphere, which allows for diffraction limited imaging. So you're not limited by Earth's atmosphere, you're limited by the instrument's own optics itself. There is no atmosphere to account for. And we're focused on weak gravitational lensing observations as well. That was our primary focus. Weak gravitational lensing is a very, very, very tiny signal that is really hard to catch on the ground. And so therefore our telescope and Hubble are best suited for this kind of for these kind of images and for these kind of imaging um, to get above the atmosphere and be able to see those tiny effects. And like I mentioned before, we launched on 16th April 2023 from New Zealand, and we landed in Argentina in Patagonia on 25th May after a 40-day flight. If you go to the next slide. So, as promised, I will be talking about stabilization, how we made sure to keep it stable. Now, this telescope is hanging off of a balloon. Now, you can probably imagine this is not the most stable thing in the world. There's a balloon that's moving in the sky because of wind, and there's a telescope that's attached to it, and the telescope may be dangling, maybe moving around. There's wind, there's turbulence, there's a lot of different factors, but we have to look at different targets. We have to look at the sky for 5 minutes straight. And there was an important focus that we had to put on stability because otherwise we just put a big camera up in space um, without any real astronomical aspects to it. We were able to achieve through a triaxial system where we had a motor at the top, four motors controlling the pitch, the yaw, the roll of the telescope as well. From the top, we had a pivot. We were able to control the pitch of the telescope as well as the roll and the yaw too. And we were able to achieve 0.05 arc seconds stability for 5 minutes, which is how long each image exposed. So that's technical jargon, but imagine you have to thread a needle from 2 kilometers away. So you're holding the thread from 2 kilometers away. You have to hold it steady in the needle. That's how much margin of error we have for 5 minutes straight. That's how long you have to hold it for 5 minutes. That's the stability that we were able to achieve. And when we were testing this in our lab, when we were testing this at the University of Toronto, we were able to detect even jumps, or if a truck rolled by outside, we would be able to see the truck rolling by outside. And then we had further stabilization, if you go to the next slide, with our camera as well. So there's roll. There were two roll motors that were moving the telescope sideways. There's pitch, moving the telescope up and down, and then there was yaw as well, uh, turning the telescope around. But then within it, there was our optical assembly where we had another layer of correction. So there were two cameras. If you see FPSC and FPSC1, FPSC2, those are focal plane star cameras. They locked onto stars and they looked at where the stars moved, and they changed this piezoelectric tip tilt mirror. They were able to move the mirror to adjust for those changes, and there with that we were able to get sub-arc second stability over the course of 5 minutes. And if you go to the next slide, not sure if that might play as well, but there's a video um, showing the stability. If that doesn't play, that's fine. We can skip to the next one. But it's showing the stability as we're moving the gondola, as we're moving the outside. It's moving. The telescope is staying stable. And again, I can share those videos if anyone's interested. This was our flight. As you can see, we launched from New Zealand. We circled around Antarctica for most of our flight. We launched on April 16th, and we flew for nearly 40 days, mostly over the oceans, but also over Chile and Argentina. We were forecasted to go over Antarctica because of the winds at that time. And so we brought it down over Argentina, even though the balloon was healthy. And we were able to recover all of our data that we had because we landed on land. If you go to the next slide, it just shows another full flight map, but just another view of the map, just showing our flight map. So we launched at that time because of the winds. They were favorable and they were going from west to east. But this is just showing our flight map takeoff and our landing in Patagonia. If you go to the next slide, it'll actually show some images that we took as well. Of the Sombrero Galaxy, Tarantula Nebula, the Southern Pinwheel Galaxy, and the Omega Nebula. And if anyone's interested, you can find us on Instagram at superbit.telescope and be able to see more as well. So if you go to the next slide, now we'll talk about why we did this and what is the point and why this is going to hopefully be the future, and the benefits of Hubble and benefits over Hubble and Space Telescope. So the first thing, like I mentioned before, we're mixing the best of both worlds with cheap telescopes, but we're getting the resolution of space-based telescopes. And if anyone was to guess how much, I'll actually have that on the next slide. But I'll continue down this slide first. I'll talk about that on the next slide on how cheaper we were. We have newer technology because Hubble was launched in the 90s. We launched in 2023, and we're hoping to launch again and again and again. And we can easily improve whenever we do those launches. Whenever we do a launch, we can recover a lot of our instruments and we can relaunch them. We can try to improve on the camera technology with newer sensors every year, which Hubble cannot do because Hubble was launched once in the 90s and it still has to continue going. And we don't have to do redundancy planning. We know Hubble requires that because to fix it, you need to send an astronaut up. If we have an issue, we can bring our telescope down and fix it. And the goal is to assist Hubble, not replace it entirely, but assist Hubble with oversubscription of science requests. And we're offering a new platform for universities to conduct science, and be able to do it in a cheaper method, not to spend as much money as Hubble does. Now, if I go to the next slide, I'll also talk about the larger field of view in just a bit as well. But if you go to the next slide, this actually shows how much cheaper we were. Hubble was $15 billion. Our telescope was $5 million, so 3,000 times cheaper. That's one stack of those five houses, if you recall the previous view. So our goal is to help make this a platform, or continue iterating on this platform, and launching one at least every year will still be cheaper. Even if we launch 3 a year for the next 1,000 years, will still be cheaper than Hubble. But the goal is to have these launched every year, or at least every other year, and be able to assist universities and researchers to conduct in science. So the next few slides, you can quickly roll by. I'll show some images that we've taken, showcasing field of view and showcasing how we've improved upon the field of view. This is Hubble telescope's view of pillars of creation. This is actually a stacked photo. So this is a couple of photos that Hubble took because of their field of view. Because their field of view is very tiny, they're only able to look at a small portion of the sky. If you go to the next slide, it'll show Superbit's view, and we're able to actually see well beyond what Hubble is able to see. And our field of view is much bigger, which allows us to study a lot more and be able to see a lot more, especially for things like nebulas, things like globular clusters, which are clusters of stars, things like clusters of galaxies as well. And we're able to see and detect more outside of the central core. If you go to the next slide, there's another one as well. These are the antennae galaxies. This is showing Hubble's view of antennae galaxies, and this is our view. We're able to, if you go to the next slide, you're able to see Hubble overlaid on top. On top of that, this is Hubble. So what we're trying to do is we're trying to both not only use Hubble data to guide us, but also assist and add on to Hubble data as well, and eventually replace Hubble with the larger field of view, so we can study a lot more and get the resolution down to the core of different astronomical objects that we're looking at. So if you go to the next slide, the next step is gigabit. This stands for gigapixel class balloon-borne imaging telescope, where we'll have a gigapixel camera. We'll have a resolution that is going to be rivaling Hubble's, with an 82 times greater field of view than Hubble, so we can study a lot more. And this is again with the same team. We're currently designing this at the moment, and then we'll be into the building phase. And the goal will be to have this open to public scientists to suggest targets, and we'll act like Hubble in scheduling different targets, and essentially trying to be a replacement for Hubble. in the near future. If you go to the next slide, if anyone's interested, there was a documentary that the University of Toronto put out. It's available on bit.ly/superbit-documentary. And I'll end off with a thank you. Thank you for inviting me. I hope this was useful to showcase some of the research that we're doing as well. If anyone's interested in learning more about it, if you're interested in learning how you could also be a part of it as you're approaching as if someone's looking into grad school, or if you're just curious to learn more, if you just want to chat, you can reach out to me on Paracha. And again, thank you very much, and I'll invite if there's any questions.
Thank you, Emaad. That was a great presentation, and I will repeat the questions to you in case you can't hear them. Oh, never mind. Almost got another slide.
Perfect.
It's okay if I put on the camera, maybe?
Jazakallah for the presentation. It's I mean, mashallah, it's brilliant. You have I mean, the helium. I guess it's echo, but the helium. This is unmanned, and it's way up in space. So, is it time to bring back hydrogen instead of helium?
The problem with that is, of course, when you're up in the stratosphere, there's no danger. The problem is bringing it up. Unfortunately, with NASA, so the balloon is made. NASA is the one that actually launches the balloon. We build the telescope, and a big organization has a very, very, very rigorous safety procedure. It's really hard to get any word of helium in. They are currently working on it. They're currently working on creative, safely filling up balloons with hydrogen. However, at the moment right now, because there's way too much risk and more on the conservative side of risk. So even if there's a very minor chance of a small, we'll say no. So at the moment it is helium, but they are currently looking into how they can fill with hydrogen.
And you mentioned there's that's 4 cameras for stabilization, 2 of them looking at the specific stars.
Mm-hmm.
What are the other 2 cameras doing?
Mm-hmm. So if you go back to the slide, if you go back to slide 21, I can show over there. So there's 2 that are in the optical assembly. Right there. Yeah, perfect. So there's the focal plane star cameras. Those are in the optical assembly. So they're actually inside in the lens stack. But then there's actually 2 outside. So if you see where the tube is, where the camera tube is, sorry, where the telescope tube is, one is actually facing, one is parallel to the tube, looking up into the sky, and the other one is perpendicular. And the reason for them is they're also both locked onto stars. So they're locked onto their own individual stars, and they're again tracking where the stars are moving, and they're sending that feedback down to the motors, and the motors are then correcting for the movement of the sky. So those are where those other 2 cameras are.
So all 4 cameras are like star like seeking cameras for civilization.
Correct. However, we only use 3 of them. We only use either so we use the 2 cameras outside, but then in the lens stack we only use 1 of them because we only need to use 1 of them, and our field of view is only big enough to allow for either one of them to hop onto stars or to lock onto stars.
And if the sun is shining, it doesn't affect the accuracy or.
We do not image while the sun is shining. When the sun is shining, it is too bright. Our research is looking into very, very, very tiny effects, gravitational lensing effects. And I know there was a previous discussion around dark matter. Our research is looking for those tiny effects because of dark matter. Light that is behind dark matter that is coming to us may have certain lensing effects because of the gravitational effects of dark matter. And that if any, that we want to ensure that is extremely dark and we have no light from the sun that is affecting it. So we ensure we do it during the night. During the day, we still use the sun, but to charge our telescope.
Okay, but like if just the civilization cameras, would they also be effective when the sun is shining?
No, when not necessarily. They can be. We have not tested that. However, when the sun is shining, we actually have another thing at the back of our telescope. We have a sun sensor, and so it scans, it turns where it is the most brightest. We actually use the sun sensor to lock onto the sun. If you go back 2 slides, you'll actually see the telescope. Um, there you go. So the solar panels are actually facing back, and the sun sensor is at the back. So the sun sensor actually looks for where the sun might be during the day, and then it stays in a way where the telescope is just focusing out front. The sun sensor is out back. We have not tested whether we can lock onto stars, but those two outside cameras should easily be able to lock onto stars. So we should be able to take images, and we did take a few images during sunset and sunrise. So they are able to lock onto stars. It's just that they wouldn't give us the astronomical data or astronomical information that we need.
It's tough.
Assalamu alaikum. Thank you so much for the talk. I wanted to ask, since you talked about, I think you said gigabit, correct? The next project. I wanted to ask,
Yep.
since there is a certain limit for superbit, which is at, I think 40,000 meters, are you aiming for a similar height for gigabit, or is it going to be like a higher height or something? Because it's already so more powerful than superbit, which I'm assuming means more equipment, so more weight and stuff like that. So I was wondering, like what would it be at the same height as superbit?
It would be, yes. The height is actually limited by the balloon size. These balloons are called the super pressure balloons, that are made by NASA, and their operating altitude is actually not 40,000 meters. It's around 33,000 meters. So in feet, it's around 108,000 feet. That's how high they go with a full load, which is around 1.5 tons. Um, that's the range that we'll probably be looking at. Our improvements on the telescope are more on the mirror, which is now going to be a 1.34 meter mirror, and the camera as well, which is going to be a gigapixel camera. Not necessarily the height, which wouldn't really gain us much advantage either.
Okay, thank you.
Man, I think we're all good. That's all the questions we got. Thank you so much again for joining us. It was a great presentation, and Jazakallah khair. Hopefully we'll get you again another time. Thank you so much.
Perfect. Thank you very much.